Today we're going to have a presentation on effect size and effect modification. So here is a quick roadmap for our session. We'll begin by understanding why effect size and why effect modification are important for us in research. Then we'll define effect size, we'll define effect modification, give the different types, give practical examples on how we can detect effect measures and effect modification. We're going to look at a brief differentiation between confounding and effect modification. At the end, we're going to have an example. To finish, we're going to end with a summary. So these are our learning objectives. First, by the end of this session, we are going to be able to define and explain the concept of effect size and its relevance. We're going to be able to identify and interpret the common effect size measures. We're going to be able to define effect modification and distinguish it from confounding. We're going to be able to detect effect modification in the study, and we're going to see how these concepts can be applied in real-world cases. So before we get into the definitions of what effectively are effect size and what effectively are effect modification, we're going to take a moment to understand why we need to know about the effect size and effect modification. So the first point that matters for us in knowing effect size is that it enables us to understand the difference between statistical and practical significance. So let's say, for example, we would like to investigate two new antihypertensive drugs, A and B, in a population of 10,000 patients. So when we administer drug A to 10,000 patients, we collect our data, we analyze, and then we have our results, which tells us that the association or whatever results we find out is statistically significant. We obtain also an effect size measure, which indicates an effect size reduction of the blood pressure by 1 millimeters per mercury. For drug B, we do the similar procedure. We administer the drug to 10,000 patients, and our results also come out to be statistically significant. Let's remember the sample size is very big, so big sample size mostly results to statistical significance. So both of our trials gives us statistical significance, but the difference here is at the level of the effect size, of the magnitude of the change of the association that we observe. For drug A, we observe a 1 millimeter per mercury difference in the blood pressure for our patients, while for drug B, we observe a 10 millimeter mercury difference. So both of these values are what we call the effect size. It's kind of a quantity. It quantifies a magnitude of a difference or a relationship between two variables. In that, the first importance is that it helps us to distinguish between what is of clinical or of public health relevance. In our previous example, if we are to manufacture this drug A or drug B, with the results of our effect size, we will consider manufacturing more of drug B because the effect size is bigger than for drug A. But in public health, sometimes we have situations where even if there's a small change, significant, when the magnitude of the effect size is also small, it also has it's also of big importance, because in urgent situations or emergency situations, like for example during COVID, where we're looking for vaccines, if we had a small effect size of, let's say, 1, and for a given vaccine, and we will not be neglecting that vaccine, because the effect size in that case really helps to indicate the importance of the vaccine. So the second importance of determining this effect size for our studies is that it's essential for evidence synthesis. Mostly we use effect size measures to compare studies. For example, in systematic reviews, in meta-analysis, we use a lot of effect estimates like risk ratios and odds ratios, quantity. It helps us to make these comparisons between studies and to put also our studies. So next, we're going to look at why does effect modification matter. We are going to take the similar example with our antihypertensive drug B, which showed us previously which shows that it lowers our blood pressure by 10 millimeters per mercury on average. But we realized that we wanted to stratify this population into by the gender, into men and women, and we noticed that for men, the specific effect measure in men for the blood pressure was 12 milligram, and women was 4 millimeters per mercury. So if we have to interpret it, we are going to notice that if we only look at the average effect, that is the crude effect, the overall effect, we might conclude that, okay, drug B is a great drug, it works for everyone. But with the help of effect modification, we see that the drug is more effective in men than in women. So we like to, the application would like to distribute this drug more to the men than to the women. So knowing this importance of knowing for whom an intervention is better, which is indicated by effect modification, we are able to prevent, like we said, misleading average effects, and it also reveals us the values for subgroups, and tells us subgroups differences. So it's really important for us to always try and determine if a variable is an effect modifier or not. Secondly, it is used to take decisions for personalized medicine or precise public health interventions. So, like we said, most of times in medicine, we prefer to move towards the people that benefit more from an intervention than the people that do not. So effect modification directly answers this question, this public health question. Thirdly, it distinguishes between real variation and bias. So unlike confounding, which is an error, which is a bias, effect modification is a real indicator of heterogeneity that must be reported. So each time we come across an effect modifier, we must always report it. So to summarize, why is it important for us to study and to report not only the statistical significance, but also practical significance, is that the p-value, which is our statistical significance, it says only if an effect exists or not. Is this effect real or not? The effect size tells us how big this effect is, and the effect modification tells us for whom or when this effect applies, this difference applies. So for a good decision making, it is always good to work with all the three of these values. So coming on to the definitions of what effect size is, we'll simply define effect size as a quantitative measure of how big a difference, an association, or relationship is between two groups or variables. In other terms, it tells us how much does X affect Y. So we are mostly used to this 2x2 table of case, control, exposed and not exposed. We're going to mostly have our examples based on this 2x2 table. So how do we concretely have an example for how effect size can be determined in a study? So let's say we have a study of 1,000 people. One group is unvaccinated and the other group, we give the vaccine. When we carry out our study, the results tells us that out of the 1,000 people, out of the 500 people, only 100 people got the infection for the population of those that were not vaccinated. And for the population of those that were vaccinated, we had 50 infections out of 500, which gives a result of 20% and 10% respectively. So what happens when we calculate our effect size measures for each of these groups? For the vaccinated, when we calculate the risk ratio, which is principally the exposed minus the unexposed, we have a risk ratio of 0.5, which means that the vaccinated are half as likely to get infected. When we calculate the risk difference, we're going to have a 10% point, which indicates that vaccines prevent 10 cases per 100 people. When we calculate the number needed to treat an NT, we notice that when we vaccinate 10 people, we prevent 1 infection. So this vaccine trial is let's say statistically significant, but more importantly, the effect size tells us that the vaccine cuts infection risk in half and prevents 1 infection for every 10 people vaccinated. So here, the magnitude of the values, the quantities of all our effect size gives us kind of indication of what is happening in our population for our study. So we're going to have the formulas and everything in details in the further examples. So depending on the research question, effect sizes can take many forms. So we're going to look at the 3 main groups of effect size measures, which are also called effect estimates, which are the absolute effect measures, the relative effect measures, and standardized measures. So the first group are the relative measures. Here we use relative measures to compare ratios between groups or proportions. It is mostly used for cohort studies, case control studies, or random control trials. Examples of relative measures are what we most commonly know. We have risk ratios, we have odds ratios, and when interpreting these values, these effect size measures, it simply tells us a story about how many times more or less an event is likely to be or not. So in this table, we can see a brief the formula on how to calculate the relative risk and the odds ratios. Next, we're going to look at the absolute measures. The absolute measures help us compare differences between groups and proportion also. And examples are risk difference and mean difference. The difference between relative and absolute measures is that the absolute measures tells us the real world difference because it shows the difference in risk or outcome between 2 groups. And it is more useful for interpreting the impact in clinical cases. So the the interpretation of for absolute measures tells us how much higher or lower an actual risk or outcome is. So for example, if you have a risk difference in a study of let's say 10%, it will mean that we have 10% more chances or lower chances of that outcomes occur or not. Lastly, we are going to look at the standardized measures. Here we use standardized measures when we want to compare effects across different scales or studies, such as in meta-analysis or in social science research. So here we have, for example, CRENC-IeDEA, which is common. We have the correlation coefficient, which is common for regression, and we have the beta regression coefficient. So we interpret standardized measures by how strong the relationship is in the scale. For example, if we have a study where we calculated the CRENC-IeDEA and we have a value of 0.8, it indicates a large effect. So for each of these measures, we have a table. We have a table where the values for each, the values and the scales for each measure is indicated. So here's a summary of the effect size measures. Here we have the type, the example, and the case used, and what it determines. So we said, like we said, for relative measures, the examples were relative risk and odds ratios, mostly used for cohort and case control studies, and it's useful for risk comparisons. Absolute, which is mostly used for public health and real world impacts. It's mostly used in trials and surveillance. And we have lastly standardized measures like CRENC-IeDEA, which is mostly used in meta-analysis to compare skills between studies. Next, we're going to look at what is effect modification. So effect modification tells us simply when an effect is different for different groups. So we are mostly used to this flow diagram of exposure, outcome, and that variable that could be a confounder, a mediator, or a collider. So in this case, let's consider that variable being the effect modifier. We notice that the arrows are not pointing the same, like in confounders and mediator and colliders. And this is because effect modification does not influence the pathway, the flow of the relationship between the exposure and the outcome. It's mostly influenced in subgroups for the exposure. So let's have a brief example for what effect modification is. Let's imagine we have a study with 2,000 participants testing for the effectiveness of a flu vaccine. So when we look at this overall, this combined result or crude risk ratio, we realize that amongst the 1,000 people vaccinated, 100 get flu, that is 10%. Among 1,000 unvaccinated, 150 get the flu, that is 15%. This gives us the crude risk ratio of 0.67. So this is how it's calculated. At first glance, it means that the vaccine reduces flu risk by about 1/3. That is 33% of lower risk of flu compared to the unvaccinated. But what happens if we stratify the population, our population, into two different groups based by age? So we stratify stratified our population into younger adults and older adults. In the younger adults, we noticed that 4% of the vaccinated get the flu compared to 10% of the unvaccinated. So the risk ratio here is 0.4. So the vaccine here is very effective and indicates that 60% it reduces the risk of flu by 60% in younger adults. In older adults, we have 16% of vaccinated who got the flu compared to 20% of unvaccinated. So the risk ratio here is 0.8. Here it makes the effect weaker than in the younger adults, because when we calculate the effect estimates, we notice that the vaccine reduce only 20% of risk of flu infection for the elderly. So what does it mean for effect modification? It means that age modifies the strength of the effect, and that is what is called effect modification. And it is important because the overall result showed us a 33% risk reduction, which could make us think that the vaccine works equally well for everyone, but only by stratifying do we see that the benefit is much greater in younger adults than in adults. So now we're going to look at how to detect effect modification. There are several ways that we could identify effect modification in our studies. The first way is by using stratified analysis. So what happens in stratified analysis is that we divide our data into subgroups, like in the previous examples, based on the potential modifier. We compare the effect estimates, like the crude risk ratios, the crude risk ratios and the risk ratios for each stratum. And if the effect differs meaningfully between strata, then the effect modification is likely to be. Secondly, we could use regression with interaction terms. In the regression model, we need to add an interaction term, which is represented by exposure times modifier here. So mathematically, we can see this short formula where we have the outcome, the exposure, the modifier, and the interaction term, which is exposure times modifier. So if the interaction term is statistically significant, it suggests an effect modification. So this regression can be carried out with any statistical software that we know. For example, we can calculate it and determine our interaction terms with SPSS. We can use R, we can use data, we can use Python. It's easily computable with the help of statistical softwares. Thirdly, we can use interaction plots. This also is done with the help of statistical softwares. We need to plot the outcome on the y-axis, the exposure on the x-axis, and then we draw the lines for the variables, for the variable which is the effect modifier. So if the lines are parallel, we say there's no effect modification. But if the lines are crossed or diverse, it indicates that there's a presence of modification. So to the right, we can see a series of interaction profiles of how it shows. So we can see that in the second square, we have no effect modification for that given variable, for that given effect modifier. And for the rest, which is either diverged or crossed, all of those indicates effect modification. These interaction plots are also possible to be illustrated with the use of our statistical softwares. So basically, In order to detect our effect modification, the first step will be to do an intensive literature research to determine which variable is likely to be an effect modifier in our study. We either stratify this data by the suspected effect modifier, and we look and compare the risk ratios or the estimates or the effect estimates for each. So here we have a table which displays the basic differences between effect modification and confounding. So we have a difference by definition. So what it is, we see effect modification is a meaningful variation in the effect, while confounding is a distortion or a bias of the true effect. Effect modification shows how the effect varies by levels or subgroups in a variable, while confounding creates false association or exaggeration. We detect effect modification by stratifying or adding interaction terms, and we detect confounding by comparing the crude and the adjusted effect estimates. We interpret effect modification by interpreting the differences in the stratified estimates, and we interpret confounders by interpreting the control estimates. We would like to always report effect modification in our studies, while confounding, we need to control for them. We need to deal with them, we need to eliminate them. An example for effect modification is that it can tell us in which group a vaccine works better, while in confounding, it can tell us that age falsely appears to affect vaccine when it is not the case. So here is a short decision tree for evaluating confounding and effect modification. So like we said, we first calculate the adjusted estimate of association between the exposure and the outcome of interest. That could be our odds ratio, our risk difference. We stratify the data based on the potential confounder or effect modifier. We calculate the estimate of association. We compare the stratified estimates using the test of homogeneity. And when we realize that our estimates are the same, we have to calculate an adjusted estimate using Mantel-Hampton method. 2 weeks ago, we had a presentation on how this was done for confounding. But when there is when the effect estimates are different, it indicates the presence of effect modification, and we need to report what we have in our stratified estimates. So lastly, we're going to have a case application. So let's say we have a research question which states, does alcohol consumption increases the risk of lung cancer? So let's test whether alcohol increases lung cancer risk. In the crude analysis here, we see alcohol drinkers had a risk ratio of 1.5, suggesting that there is a 50% higher risk of lung cancer. At first glance, like we can think that alcohol drinkers appear to have the 50 higher risk of lung cancer alone. But what happens when we stratify our analysis by the smokers? We have read our literature, and then we have noticed that smokers, whether you smoke or whether you don't smoke, can act as an effect modifier. So we should decide to stratify our data by smokers. So we realized that among smokers, alcohol makes no difference. Both the drinkers and the non-drinkers have about 16% risk of lung cancer. That is a risk ratio of 1. So among non-smokers, interestingly, alcohol drinkers appear slightly less to develop lung cancer with a risk ratio of 0.74. So what is happening here? Smoking distorts the true estimate. So that is confounding. But smoking also changes the relationship between alcohol and cancer in smokers, in non-smokers, compared to smokers where we see no effect. In non-smokers, maybe the non-smokers, the fact that you don't smoke can be a protective effect. So here it helped us to determine what was a protective effect even in our study, and that is effect modification. So once again, this is why we always need to consider both when carrying out our analysis. So some variables bias the effect, others truly change the effect, and sometimes the same variable can do the same, can do both. That is, be an effect modifier and a confounding at the same time. Okay, so what happens when we have the case of a confounder being at the same time an effect modifier? What we do is that, like we know from our tree decision, we have to calculate the estimates of association for each strata, and then when we realize that it's a confounder, we compare the adjusted estimates and report it. And in this way, the fact that we're reporting it makes us it's the way that we need to do when it's an effect modifier. So by stratifying our data and reporting it, we are controlling for the confounder, and we're also reporting for the effect modifier at the same time. So to conclude, we have we can say that effect size is the same as the strength of association. We have several examples that we know. We have odds ratios, we have risk ratios, we have mean difference, we have cohency. Depending on our study, effect modification tells us for whom or under what conditions an effect occurs, or is higher or lower, and both are important for accurate interpretation. And lastly, so it's always important to report the effect size and modifiers in our studies and not just the p-values. So here are some of the references which we use for this presentation. Thank you for your kind attention.